right, with absolute value, we're going to generate two different equations just so we can get rid of the absolute value. So we have x squared plus 4x equals positive 5, and x squared plus 4x equals negative 5. And then we're going to solve for x in that case. So here we, in both cases, bring the 5 over. Actually, yeah, see, let's do completing the square. Let's do that. So 4 over 2 is 2, and 2 squared is 4. So I get x squared plus 4x plus 4 equals 5 plus 4. And do that same trick over here. Oops, plus 4. It's negative 5 plus 4. Let's see, so on the left side we get x plus 2 squared equals 9, and here we get x plus 2 squared equals negative 1. Okay, so we're going to have some imaginary solutions here. And then we'll take the square root of both sides. So I get x plus 2 equals plus or minus the square root of 9, which is 3. And x plus 2 equals plus or minus I. Okay. So we bring the 2 over, so negative 2 plus or minus 3. Negative 2 plus or minus I. And on the right 2, we actually got our solutions there, but this side will split up. So negative 2 plus 3, negative 2 minus 3. Okay, so our four solutions are a positive 1, a negative 5, a 2 plus I, and a negative 2 plus I, and a negative 2 minus I. Would be the four solutions we get out of that equation. Okay, number 18, again, we're going to set up two equations to get rid of our absolutes values. So first we keep everything positive. So x minus 1 equals 2x plus 5. And then we make one side negative. And then we just solve each equation independent of each other. So over here on the right, on the left one we get, let's see, so let's subtract x from both and subtract 5 from both. And we end up with a negative 6 here and an x there. All right, so one of our solutions is negative 6. Over on this side, let's see, we get x minus 1 equals negative 2x minus 5. So in this case, let's add 3x to both, add 2x. And let's add 1 to both sides. So we get 3x equals, that's supposed to be a 2, equals negative 4. So I get x is negative 4/3 and the other negative 6 from the earlier piece. Alrighty, number 19, my first task is to isolate out the absolute value. Once I've figured out which type it is, then I can decide which method I want to do to get rid of the absolute value. So I'm going to add 11 to both sides. So 3x plus 2 is greater than 16. Okay. Now, it's greater than a positive number, which means we're going to break this up into the OR statement. So I'm going to break this up as to 3x plus 2 is less than negative 16, or 3x plus 2 is greater than positive 16. And then I'm going to solve for x. So 3x is less than negative 18. Divide by 3, and so I get x is less than negative 6. On the other side, again, subtract off the 2. So I get 3x is greater than 14. And divide by 3, and I get x is greater than 14/3.
Okay, so in interval notation, I have it going from negative infinity up till negative 6, union 14/3 going out to infinity. All right, number 20 is kind of a little bit more abstract than what normally shows up in pre-cal, but it's great practice for a concept that shows up in calculus. So there's no reason at all why we can't get used to this strange-looking E symbol called epsilon. What we're going to do first, first off, I see the 1 minus 7, so I can clean that up a little bit. So that's 2x plus, so it's 2x minus 6. It's less than epsilon. All right, it's a less than case, which means I'm going to break it up into a 3-part inequality. So a negative epsilon less than 2x minus 6 is less than a positive epsilon. And then I'm going to solve for x. So I see that I can add 6 in a 3-part inequality. I want to add 6 to everything. Now, epsilon is just a generic variable, so I have no idea what epsilon represents. So I'm not going to combine it with the 6 other than, say, 6 minus epsilon. No, well, 6 plus epsilon. And then I can divide everybody by 2. And so there's actually our interval right there. So for whatever reason, 6 minus epsilon over 2 to 6 plus epsilon over 2. So just isolate it out, not too bad. Okay, number 21, we've got a polynomial inequality. So I want to first get it into standard form with the polynomial characteristics on the left and 0 on the right. Translation, bring over the 4x and the 15. So 4x squared minus 4x minus 15 is greater than or equal to 0. All right, then I want to factor this. Figure out where it actually equals 0. So let's see. Let's try 2x and 2x, and I'm guessing a 5 and a 3. Is that any way to get a negative 4 out of that? So 2x times 2x is 4x squared. 2 times 5 is 10. 3 times 2 is 6. Ooh, 10 and 6. I can see a way to get a 4 out of that, and I want that negative. So I want my 10 to be the negative and my 6 to be the positive. So there we go. Which tells me that my solutions for this equation then would be negative 3/2 and 5/2. Okay, so what we're going to do is call this sign test. Or I'm going to pick values within each interval piece of the number line that I just created. And again, what's so special about those two numbers? Those two numbers are where this polynomial happens to equal 0. So what's going on each side of those two numbers? So for example, if I go something like negative 2, or something like 0, or something like, let's see, 5/2 is 2.5, so if I pick 3, right, what's this polynomial doing at those test points? Okay, so I'm going to evaluate this factored form of 2x plus 3 and 2x minus 5 at those test numbers. And let's see, so if I do, so 2 times negative 2 plus 3 times 2 times negative 2 minus 5. Well, here I get a negative and I get a negative, so that generates a positive value. So that means my y values are above the x-axis at that point. If I put a 0 in, so 2 times 0 plus 3 and 2 times 0 minus 5, I get a positive and a negative, so that means my y values are negative. And if I evaluate it at a 3, so 2 times 3 plus 3 and 2 times 3 minus 5, I get a positive and a positive, which means it's above. Okay, and so I am looking for what? According to our
symbol there, I'm looking for things that are greater than or equal to 0, so I want all the positives from that number line. So the interval, or the solution set for this, would be negative infinity up till negative 3/2, bracket, union, bracket, 5/2, up to infinity. All right, number 22, we're looking at the rational case of our inequality. So in the rational case, we are looking for where the numerator and denominator are equal to 0. So 2x minus 1 equals 0, and x plus 9 equals 0. So hopefully you get 1/2 and negative 9. So on my number line, those are the two places where this polynomial can switch from a positive y value to a negative y value and vice versa. Okay. We'll eventually go back through rational function characteristics and properties, but you're looking at the x-intercept and the asymptotes for those two numbers. All right, so I need to pick some test values. So something like -10, something like 0, something like 1. Just a clear number that's in that interval. And I'm going to evaluate our rational function at those numbers. So 2 times -10 minus 1 over -10 plus 9. And up top I get a negative and a negative, so that's a positive y value. If I evaluate it at 0, so 2 times 0 minus 1, 0 plus 9, I get a negative up top and a positive in the denominator, so I get a negative result. And then we'll do the 1. So 2 times 1 minus 1, 1 plus 9. So I get a positive, which means my y values are positive again. Okay, and what am I interested in? I am interested in the negatives. So what interval do I get negative y values on? And that's anything between -9 and 1/2. And then we have brackets on this, but we got to remember that anything that came from the denominator we can't actually include. So that gets a parentheses and the 1/2 gets a bracket. And that would be our solution. Okay, in dealing with radical equations, two ideas that are real quick to have sort of in our pocket so we can do them. Just to remind ourselves of our factored form of a plus b squared. We get a squared plus 2ab plus b squared. So that real quick simple idea is going to help make this radical stuff go a lot quicker for us. And then the other concept is whenever we're to get rid of a square root, we got to square things. And negatives, when you square them, tend to become positives. So it's very easy for a number to show up as a solution that really isn't a solution because that whole negative squared becomes a positive idea. So anytime we are dealing with radical equations, we want to go back and check our answers and make sure that what we think is an answer actually is an answer. Okay, so number 23, I want to isolate out the radical first. So I want to subtract 1, which gives me the square root of 5 minus x equals x minus 3. And then I want to square both sides. So on the left, I get 5 minus x. And then this is where that factoring pattern is going to kick in for us. So it's something squared, in this case minus 2 times something plus something squared. And then I just fill in the blanks. So we have x's there and 3 there, and that minus is what makes this minus in front of the 2 show up. So when we simplify all this, we get 5 minus x equals x squared minus 6x plus 9. And then I want to move everything over, so I have it set up in a quadratic. So x squared minus 5x plus 4. And then I just want to solve. So factor, let's see, x minus 4 and minus 1. So for our solutions, we get 4 and 1. Okay, so before we get too excited, we want to come back and double check this. So let's plug a 4 in here. Just kind of talk this through. So 5 minus 4 is 1, and the square root of 1 plus 1 is 2. Okay, so we get 2 on that side. 4. Okay, so 4 works. And let's check the 1. So this 5 minus 1 is 4, so square root of 4 is 2, 2 plus 1 is 3, and 1 minus 2, oh, you see the problem? 1 minus 2 is a negative 1. So only the 4 checked out, so only the 4 was a valid solution.